Good afternoon. My name is Myrick. It's a pleasure to be here with you today. I want to talk to you about exploring distributed sensor synchronization with GNU radio and RTL-SDRs. And this is without hardware modification. You'll see what I'm talking about in terms of what we're trying to do relative to that topic later on. I represent INSCO. We deal with a lot of synchronization issues of having to deal with that because we are in the segment of the space of dealing with GPS-denied environments. So in GPS-denied environments, of course, when GPS is gone, you have to rely on your own systems to be able to synchronize and figure out what's going on. And we specialize in DMR type of hardware, and that's distance measuring radios. And so this talk I thought would be great to bring about some aspects of the overall concept of synchronization and what does it mean relative to using that within the GNU radio framework. So I wanted to talk a little bit about the journey of how I actually got here. A lot of times when you talk to people about GNU radio, there's a story behind how they actually got here. And so I decided to at least try to capture as much as I could in terms of the story of actually how I arrived. Now what you see there is a GNSS based GNU radio system that has 4 RTL dongles there that are used to capture, actually capture the GPS signal. But there, that's sitting inside of a seat of the truck. And I decided not to try to drive from Virginia to here to actually collect data and then show you results. But I figure I could at least capture the moment of what I actually set up in terms of this whole system. So let me give you a background about me. I had a chance to work under Dr. Michael Zoltowski and studying adaptive array antennas and GPS anti-jam antenna processing. And so a lot of what we focused on was subspace signal processing. And subspace signal processing, if jammers are changing very rapidly, you have to be able to adapt and be able to compensate for the jammers while minimizing distortion on the GPS signal. And so from that research, I was able to sort of get my bearings straight in terms of what I wanted to do relative to signal processing. And then you can see, around 2001, GNU radio had the initial release. I sort of knew about it, but I didn't have a chance to really experience or use it yet. And so through 2001, 2013, I started working on a job, and the first thing he did for me was they gave me a set of data, and he said, find what's in the data. So no information, hardly anything about what was going on in there. And so I learned quickly that when you're dealing with real data compared to what you studied in the textbooks, it's a whole different world, whole different problem. And one of the things I guess I learned from that, from 2001 to 2013, is that really as a student, for undergraduates and for graduate students, you really want to get involved in looking at live data as soon as you can, capturing data and applying those theories that you're learning in the classroom as soon as you can. Because what it does, it gives you some type of, it gives you that extra level of understanding that you need to deal with real world problems. And so from then on, 2013 to present now, I was able to sort of get a chance to look at GNU radio. I got exposed to the RTL-SDR, and I also started looking at the Jetson TK1 platform. That's a GPU-based platform, has 192 cores. And one of the interesting things I said, well, you know what? After all of this and all this experience, why not combine GNU radio with the Jetson TK1 with the RTL-SDR and come up with a processing system that one could explore, capturing different data, SOAP data, GPS data, and begin to understand concepts that are associated with synchronization. And so that's sort of what this device here is now looking like, is that captured system, the system that allows you to do data capture and also to process data with the GNU radio framework. And one of the things that's important here, I want to point out, is that the underlying process of the synchronization to do anything relative to GPS, I was able to find this software package that's known as GNSS SDR. And GNSS SDR is built on the GNU radio framework. So this is an actual GPS application that uses the GNU radio framework to actually do real-time GPS positioning. And so with that, the idea and the concept is, what could I do with that particular type of framework, if I had a worst case scenario where I have all of these software-defined radio receivers that are unsynchronized. They don't have a common clock that you can actually sync up to. And that sort of leads me into this slide here. So at INSCO, one of the things we're doing is we're looking at a variety of different type of algorithms related to synchronization. And so we have a variety of software-defined radios at our disposal that are at our disposal. We have the USRP 320 actually. We have some of the minis, and we also have the red Pitaya. And for this, this is for the low frequency type of signals that we sort of like to process as well. So here what I wanted to just show is that most of the time for the hacks, there's really no way to add an external clock to the current RTL-SDR. And so with that, most of the time when people try to use that for multi-channel processing, multiple elements in terms of the antenna, they tend to try to take the crystal that's there and share that among the other RTL-SDRs. And you could do that to a certain degree, and you can come up with different scenarios. But what ends up happening is that there's only a certain level of synchronization that you can actually have. And I love the talks earlier where they talked about time, frequency, and phase synchronization. And this is what it boils down to. Understanding how to actually first get your time offset, then understand the frequency offsets, and then figure out from there how to extract the phase. And so this is one reference that's out there. It's called the multi-RTL. You can go online. You can actually look this up on the link there for actually the software. And if you go there, what you'll find is that there's a whole string of comments where people are just talking about how do I use these RTL-SDRs as a multi-channel system. And so most of the times you see, the comments, they're talking about things, but they really stop at the level of being able to synchronize in time. When it starts getting to frequency and to phase, it's sort of like, well, I really don't know what to do or how to get there. And so I looked at this and said, wow, this would be interesting if we could figure out a way to do some kind of transformation up front of data that's coming from the RTL software-defined radios, and before they enter into this sort of GNU radio framework, to sort of precondition it. And then maybe I could do some cool things with phased array processing associated with GPS. And that's sort of where the idea came from, and these are some early concepts that I wanted to share with you today about that. So really, where am I starting? So a couple of years ago, I did a collect with the software-defined the software-defined radio receivers here, and I was looking at FM radio. So FM is interesting because right now there's HD-FM. And HD-FM actually has an analog portion and it has a digital portion. And I was curious about the OFDM portion that is the digital portion of the signal. And so with that, I started noticing that I could actually take two RTL-SDRs and come up with ways to actually find the clock drifts between two of them and compensate for them. And then I could actually apply adaptive array processing on top of that. And so with that, that led me to say, I wonder if there's a way that I can characterize the RTL-SDRs with a system that will be running on a Jetson K1 to stream the data and then use a GNU radio-based GNSS SDR system to then sort of get an understanding of what can I do with these dongles that are not connected physically in terms of having a clock or actually having a common clock. And so from that, I started going down this sort of research area, and I got exposed to the GNSS SDR framework. Now, this framework allows you to implement your own algorithms, and again, it's based on the GNU radio framework. And what they've done is that they've taken all the complications of terms of having a GPS receiver, mapped it, used GNU radio as the framework, and allows you to go through the different segments or aspects of a GPS receiver. For a GPS receiver, you have to synchronize, and you have to demodulate the information in order to find your position. And so with this, I thought this was a great framework to start off as is, okay, let me see if I can use this to show the capability of what we can do from an algorithms perspective with the GNU radio. So a lot of the work we've done in the past, I've shown results where I would do some type of interference suppression. And we're big at INSCO on doing the algorithm development. I remember Tom Rondeau was talking about algorithm development side to deal with hardware impairments. And we're big on that. What can I do on the algorithm side that can support the cheapest hardware to the most expensive hardware? And being able to understand the various algorithms that are available to you to be able to do that provides a lot of insight into solving some very, very challenging problems. And so that's sort of where we are in this space. So I was using this actually as a processing. After I did my pre-processing, I would clean up the jammers, get rid of the jammers, and I would send it through the GNSS framework. And I was able to show our customers that, hey, here's a framework here that before jamming, you could see that you couldn't decode anything, you couldn't get any kind of position information. And then after our process of pre-processing and cleaning the data, while at the same time minimizing distortion for GPS, I could show improvements. And so already that was a win for us in terms of being able to leverage the GNU radio framework in that particular construct. So what am I talking about when I say synchronization? So I'm saying software synchronization. What is that saying? That says that I have no hardware inputs that I can leverage with my clock. So I have free running clocks on all of the RTL dongles that are there. And so what do? Well, I look at it as a point of reference where if I can at least take one of the dongles, use that as a reference, and then slave all the other ones to that as a reference, then at some point I at least can get the offset information. But in order to do that, I still need to have a signal that is available to me, which is what I'm calling a signal of opportunity. And that's what the SOO is there. And so we came up with this construct of having a signal of opportunity. If I have asynchronous snapshots that go into the buffer, first doing a coarse synchronization extraction, and then doing a fine synchronization extraction. And it pretty much parallels what you would normally do within a GPS receiver. It's just that I'm using the SOOP as my signal to try to do that. And so I said, well, before I even go down the road of SOOPs, what is the best signal that I could use to actually test whether or not I'm doing well and to sort of help tease or help people understand what the concept is in terms of being able to synchronize with these distributed nodes. And so what I decided to do was, well, let's just look at the GNU radio within the GNSS SDR receiver, and let's just look at the GPS signal itself. Let's take the GPS signal, and let's just use that as a reference to try to show proof of concept what one can do if you wanted to try to synchronize with these independent nodes, and first, synchronize in time, then in frequency, and then in phase. And so what I want to talk to you about today is sort of walk through that whole concept. So this is what I used to do in terms of, I normally do space-time, I normally do STAP. STAP is what I'm big on in terms of interference suppression, tracking jammers, and things like that. So I wanted to map STAP to this problem that I have in terms of things being not quite synced up. And so what I looked at this is I'm really just mapping, once I figure out the time offset and then once I figure out the frequency offset, I'm really looking at clock drifts. And I'm trying to figure out really the clock drift between these different SDRs. Once I can figure out the clock drifts between these different SDRs, I'm able to figure out the synchronization information I need such that there's a level of coherency associated with solving a normal Wiener filter problem that I would have in STAP. Now, since my background is in subspace signal processing, for me, I thought about, well, if I want to do Wiener filtering, there's a certain level of coherency that has to occur for me to be able to null out jammers and attract jammers. And so my aspect of the research is, why not explore the level of coherency that's available based on the type of hardware that you have that's available to you? And that's sort of the logic and the flow and the thinking I'm thinking about in terms of exploring this area of having distributed sensors, but still being able to do some type of jamming and some type of suppression. So you would normally take your snapshots that you would have in your standard process, rather than assume that they're coherent, assuming they're off by some amount based on this delta drift, and then go through your standard processing of doing your inversions and your Wiener filtering. And so that sort of is the backdrop of what sort of is the concept and the idea about what I would like to do. There's a paper that we published a couple of years ago where I was showing the FM receiver problem, where I was actually trying to do something that was sort of cool, where I wanted to create a bistatic radar, passive bistatic radar, where I wanted to have a distributed set of sensors. And so first I said, why not use the FM radio station as the OFDM portion of it to first synchronize my receivers and then go back and process the analog portion to do passive bistatic radar. So that was sort of the concept there, and at least that paper gets into some of the ideas behind that. All right, so what did I end up doing? Well, I ended up creating what I'm calling this RTL-SDR based GNSS collection system. I took it, I'm running it here right now without of course, the software-defined radios that are actually attached there. But I said, well, let me do a simple array. This ends up being just a linear array. Of course, I could have done a 2D one. But proof of concept, I just wanted to go out and really just get involved in terms of collecting data. Now, I also wanted to do this. Notice that the cost of the system is roughly less than $600. I wanted to do this because I think from an educational perspective, this is great for students if they want to go out and just start collecting and understanding different signals from a multi-element perspective versus just a single SDR. And that's sort of what I was motivated by this as well. I said, hey, if I could come up with this sort of a reference system that students could learn from and others in the area could learn from, this may be very interesting just from a research perspective, because in the end, I still have to go through my synchronization process, but I have a truckload of data that I could use to help sort of get everyone in sync in terms of what's going on as far as the process. So this is a system that I had set up. I collected data. One of the key things was I wanted to be able to stream 4 RTL-SDRs at the same time, and I was able to do that for 60 seconds via the NVIDIA. I wanted to be able to demod the navigation data for each channel that's detected. So normally when you think about GPS, the channels correspond to the satellites that are available to you. And then I wanted to be able to track delay, frequency, and phase from each one. So the RTL-SDR has enough fidelity for you to actually demodulate and generate a position estimate. And so I wanted to take that information and figure out how do I now take that information and try to figure out how to solve for the time offset, the frequency offset, and the phase. And I'll show you where I am today. Haven't completely done that. That's why that's a little circle there. But I want to at least show you I want to show you the initial results that I have with that. So synchronization as a whole, when you think about synchronization, GPS is a great example because I have Doppler due to the motion of the satellite. If you're moving, you got to compensate for your Doppler as well. I have to time sync, figure out a way to get lined up with CA codes that end up being 1,023 in length in terms of chips per bit. And then on top of that, I have to figure out carrier phase so I can actually demodulate the bits and figure out my position information. So that in itself is one problem where if you were to hand that, or you had a bunch of problems that you were to hand relative to this, you would learn a lot just from synchronization, understanding that, because there's so much that's going on. So in this particular case, from the 4 software-defined radios that I had, I wanted to show sort of what was the standard approach and the approach that I'm using that's called the multi-stage Wiener filter. Now, I mentioned before that a lot of my thesis work was in subspace signal processing. One of the things that came out of that was this concept called the multi-stage Wiener filter. And it threw out some, at least concepts for you. So normally you think about the KLT in terms of decomposing a covariance matrix, and you have the eigenvectors and things like that. The multi-stage Wiener filter is actually based on decomposing what they call the Krylov subspace. So it's a different kind of subspace. And in essence, in summary, what it does, it allows you to really focus in on the information that you care about most in that subspace versus breaking it up sort of just based on power. And so there's a whole bunch of work we have on that in terms of papers. But what this shows is that with the set of data, the algorithm of the multi-stage Wiener filter subspace was able to improve upon the initial acquisition detections that were associated with the other data. And so you can just see that, I was only really able to get 4 to 5 detections from the standard correlation process, whereas with the multi-stage filter, I improved upon that to at least 6 or 7. And so again, focusing in on the algorithm aspect versus not having the best hardware, this was sort of some initial results to say, hey, wow, I can still do this even though I don't have the best hardware. There's ways within the algorithm space that I can improve upon what I would normally do with my standard processes. And so let me give you an idea of what we actually did, at least from some initial results. So I decided to let's track PRN22. PRN22, again, is associated with one of the satellites that I tracked from this previous chart that showed each one of these detections that corresponds to a particular satellite. And so in this case, I was looking at 22, and I wanted to show you exactly what goes on in terms of the synchronization process. So first of all, you have DLLs, you have PLLs. So your GPS receiver that's in your phones, it's running all of this real time. It has PLLs, it has DLLs in that, track the delays, tracking the frequencies, tracking the phase, and then from that, it's able to then demodulate and come up with what is going to be the navigation bits. So this is just end up being 1 second or snapshot of data that I have here, but I want to at least capture this for you because there's a lot that goes on within the synchronization, and a lot of times it is adaptive. It's adaptive. It's not just one shot, but you're changing as the data is changing. You have to be able to adapt accordingly. And so the concept here is if I can track all of these signals with the RTL dongles individually, I really have all of the state information at my fingertips. So at that point, really all I have to do is figure out how do I now compensate? Because what happens is if you have these 4 different dongles and they all are receiving the same channel that's coming from the same satellite, then whatever offsets they're going to have, they'll show up when you take the difference of the time, the difference of the frequency, the difference of the phase. Because you expect those to be common among the different dongles. And that sort of is the whole concept. So I was able to sort of test this out just by looking at a couple of satellites. One, PRN22, when I looked at the difference between, let's say, dongle 1, dongle 2, it had some value. And then I said, well, let me look at another satellite, in which I took the difference of that between dongle 1 and dongle 2, and they end up being the same. So that's the concept of now being able to use sort of think of the satellites as SOAPs, in this case, where I'm able to get demodulation, I'm able to demod data, able to get phase information as well, because when I'm running my PLL, I'm getting both frequency tracking and phase tracking. So now it's just a matter of me taking that and figuring out how to compensate for that within the framework. So here's one quick result I want to show you, at least from the initial time alignment. And again, there's next steps that I have to do in order to complete this process, but this is, at least is the initial concept I want to show you. So here's two sets of data where I have PRN before alignment and I have the PRN after alignment. And of course, from this view where you zoomed out, you really can't tell the differences between the clock offsets. And remember, the way I set this up for the data capture for the different dongles, I had it set up within my Jetson K1 framework where I just hit a button and said, okay, record now. Record for 60 seconds. But I don't know what time frame each one of the dongles started streaming data because they're all going via USB, so you don't really quite know. So in order to actually see that, if you zoom in, you can tell from here that relative to 1, 2, 3, and 4, you can see that they're all starting off at different times, but we're still within the millisecond framework. So the one thing you could do just based on this, once I demodulate the data, I have a nice signal that I can cross-correlate with to determine the offsets. So the time is sort of trivial, at least in this case, in terms of being able to solve it, but it at least shows proof of concept of how you get started. So now I have a baseline data set, this long stream of data that should be the same in all of the RTL dongles. Now I can use as a cross-correlation or a vector, as a reference vector, so I can reference it to one or the other dongles. And in this case, I use the RTL-SDR number 3 as my reference. And so everything will line up to that one. And then for the rest of the process, for both phase and frequency, I would do the same thing. And that's the idea and the concept. Now, you may be asking, so why do we care about this? Well, one idea I had for GPS is to come up with a GNU radio-based GPS monitoring system. Since it runs real time on GNU radio, I could actually just sit there and have it monitor the GPS spectrum somewhere, out there. Let's say I'm just monitoring, trying to figure out, are there jammers? If a jammer comes around and now I can detect that within GNU radio, I can now say, oh, let me go in and take a snapshot of data with all of the rest of the RTL-SDRs. Once I take the snapshot of data, if I can do this process post, I can combine the snapshot of data, send that off somewhere, and do another analysis to determine actually where is the jammer coming from. Because with a single antenna, I can't do that. But now if I have multiple antennas where I can figure out a way to coherently combine all of my streams that are coming in from the array, now I have both the ability to figure out, okay, a jammer event occurred, and also I have the ability to say, oh, let me line this up so now I can actually find out where the jammer was coming from. So that's sort of the concept, at least from the GPS side, and why I think this could be something that's novel. And again, another application for GNU radio, because I'm operating off of a framework that already gives me real-time data. So I want to show you a demo real quick of actually how quickly GNU radio is able to process a snapshot of data. All right, and so this is, again, the GNSS framework, and the GNSS framework is based on GNU radio, and it allows you to add in your own modules, pretty much via the C++ framework. And so what I want to do usually is to show how you can actually use this to demodulate data that's already been captured, and then eventually what I would like to do is come up with custom modules that would do the synchronization and then embed that within the GNSS framework. But let me show you an example here of data that was collected. This is actually going to be from, I sort of showed you, I think it was dongle 3. This is going to be data that's collected from dongle 3, going through the GNSS framework, and it's going to show you how it's able to demodulate it in real time. So this shows how it's starting to track. It found the different channels. Once it tracks, it has to demod and determine where the nav messages are. Once it determines the nav messages, it figures out the subframes, and then from the subframes, it's able to demodulate the data and come up with the position estimates. And so now you can see how quickly that was able to actually demod and come up with the position estimates. This, at least for a single dongle, was able to do this within a real-time framework. And so what I did was this. I want to at least show you this data. But I have gone and I have tested it and have gone out and used it within a real-time framework where I'm just sitting there, I'm just looking at it and watching it, my actual information change as I'm recording it real-time within the GNU framework. And so this is what I thought was just exciting to sort of show as a demo. A lot of times, people don't know what GNU radio is doing already within the real world, I call it. And this is one example, at least from the GPS demodulation scheme that is working well in. All right. And I'm pretty much done. I have a couple more charts I just want to show. The NVIDIA Jetson TK1. As far as setting that up, Tom wrote a nice setup here. This is where I started in terms of trying to figure out how to get GNU radio installed on this. So I started here and then eventually continued to test it and build it from scratch and made sure that I could get it to work. And then once I had that running, I was sort of home free in terms of being able to have a system available that I could capture and stream data and then do my overall sync analysis. So it's sort of the summary of where I am. I have some initial results that sort of show that at least it's feasible. I do have an embedded collection system that's running GNU radio processing. Real-time GPS positioning is possible with this system, and I was able to show that you could simultaneously stream 4 RTL dongles within the Jetson TK1 framework. So that was great. And then the potential GNU radio projects, the outer tree modules still, there's some work I think that could be done from the source that I've seen on the websites in terms of the multi-RTL. Again, there's things that we can work on. That's something I think that would be sort of neat in terms of a project. The performance approach in terms of urban environments, be neat. I have a system here that's mobile. right now is running. You know, I got a little battery pack here. I can take it out anywhere and collect data. And so it would be interesting to see for asynchronous sensors that are not synced up, how well can I deal with multipath and severe blockage. Also develop a demo with the GNU Radio app that leverages this. It'd be nice to have a framework with GNU Radio and an app around that. And then quantify and demo the level of coherency. Notice I haven't been able to get to the level of saying how well do I have to be in terms of coherency to determine my ability to actually do the stat processing that I want to do. So that's where I want to go. I want to be able to show stat processing with a coherent set of receivers, stat processing that's not coherent. How well can I get there based on the level of sophistication associated with the hardware with just software processing? That's sort of where I'm trying to go. And at least there's, if we have time for questions.
So we only have time for one or two questions, so maybe one in the back.
This question has to do generally with multi-sensor data fusion and how this process can kind of fall within the framework of multi-sensor data fusion. And I was kind of just curious if you had explored other correlation techniques such as Bayesian statistics or something along those lines to improve the accuracy of the multimodal sensors, or maybe identify which of the 4 antennas were most reliable in a given moment and then assigning that to be the reference versus arbitrarily picking one in the beginning.
That's a great question. I have not had a chance to do that. What I did do was I started looking at the differences in terms of those as a metric. So if I have all of my data tracked and I start looking at the differences between the different dongles, what I can tell is that some are better, let's say, are better tracked. Some are better equipped than others to maintain the difference. Because what I care for is really that the difference is maintained throughout my duration of my signal, right? So if I'm collecting 60 seconds worth of data, I would hope that the difference between the two dongles would be small enough, or at least the variation of that doesn't change much, so that when I do my coherent processing, I'm not having to update as much. So yeah, that's a great question. I haven't gone down that road, but I think I have some initial statistics that will feed into that based on alone looking at the differences. Between the sensors.
All right, we're out of time. I saw there were a lot of other questions for Will, so if you could follow up with him afterwards, that would be great. And let's thank our speaker.